In order to distinguish between our physical and chemical changes, we should really zoom into the microscopic level to explain it more authentically than we do with macroscopic phenomena. In other words, instead of talking about the properties that we typically observe, let's first zoom into the microscopic level where we're looking at molecules and atoms. Now, in the static picture that you see here, it's not totally authentic, and I'll point out where my sketch is not physically true, but where it's suggesting the right things. Now, here you see that our solid, we have those molecules closely spaced. And notice I said molecules, not atoms. For physical change, we're going to be focused at the molecule to molecule level. If we want to look at changes between how atoms and other atoms are sticking together, for that we need to just focus on chemical changes. In physical changes, we're leaving those alone. And in chemical change, we're saying that things are popping apart. In physical change, we're saying that those objects are strongly held, they're staying together, and instead we're focusing on how they separate from their neighbor. In other words, we're talking about how sticky they are to their neighbor. Now, we'll talk about what the stickiness entails a little bit later when we talk about intermolecular forces. For the time being, we're just going to appeal to the idea of stickiness. Now, one spot that my model is not very authentic is that the spacing for the solid and the liquid should be identical, or very close to it. There might be a tiny bit more space in the liquid than there's in the solid, but not by very much. So keep in mind that that's one thing that is inauthentic here. And with a gas, we should actually have a lot more space. Now we'll see that when we talk about the ideal gas law. We'll have a lot of space, so much so that these these molecules act like they can't even see each other, and they're not interacting pretty much at all. Now let me throw in a little bit of motion, because you can see here that I've got a little coordinate here where I'm saying that we have minimal motion going to lots of motion. And all of that is related to how much heat has been added. So in a solid, there's not going to be much motion. In fact, I'm overemphasizing it here. In a liquid, there's going to be more motion. The spacing should be closer together. They're just slipping past each other, but they're staying in contact. You can think of this as everybody sitting in seats. This is people sliding around in a very closely packed elevator. And in a gas, this would be people jogging around in a track. Very little space, immediate contact. Very little space, slipping past each other. Lots of space and nearly no contact. That's the distinction we're making for liquids, solids, and gases. Now, that's the underlying feature for all of our physical changes. With a physical change, we're going to be changing how they're sticking to a neighboring molecule, but we're not going to start making or breaking any bonds. That's the key point to make. Now let's look at evaporation. At the microscopic view, we're going to have all these things moving. The liquid is moving slower and the gas is moving faster. And of course the gas and the liquid should be moving in random patterns. Now notice that molecule right there in the oval just popped loose from the liquid in the gas phase. It had enough motion to overcome how sticky it was to its neighbors when it was sitting in the liquid. Now let's look at the reverse process. Condensation is going to be when you have your gas phase molecule. It's moving at the high speed, it bumps into the surface, and it sticks. It's going to be moving just slow enough to stick to some neighbors. That's going to be condensation. So you can see when we zoom into the microscopic view with physical change, it's all about how sticky a molecule is to its neighbor.